Hello everyone. Am I live? I think I'm live. Uh, yeah, I think I'm live. Hello, how are you, everyone? Uh, if you see the title of the stream, you probably know what we're doing. Uh, for those of you who maybe don't, we'll be implementing the DDPM paper in Python using PyTorch. I have like the paper with me as a physical copy, and I also have it downloaded. So like we'll go through it and implement. As you can see, it's a late night stream, so I probably won't go very long. I don't know. We'll see. I mean, it depends on the progress we make, kind of. If I make some good progress, then we might go for like an hour and a half or maybe 2 hours. But otherwise, I might just quit for now. Uh, and if we don't finish in this video, then I probably am not gonna guarantee you when the next video is coming out. Partly because uh, I'm doing like a lot of stuff right now on my own, and uh, I kind of don't have. Just see if this stuff is still going. Yeah, and I don't have a lot of time to make videos, so that's why I'm streaming right now. Uh, so yeah. Okay, let's just get started. So I don't think anyone's watching this right now, so it's a good thing I don't have to like check chat or anything. I can just work on my own. I had created like a yeah, I had a directory for that. So was this the directory? Yep. Okay. So I have as I said, a physical copy with me over here. I sometimes like reading it from the physical copy. Certain things. I also like made some notes and annotations on the paper. Uh, I have gone through it like once, but like all of this stuff, annotations and stuff I had made, it was all done like 7 or 8 months ago. So I am almost I'm as clueless as someone who probably doesn't know the intricacies of DDPMs. I know what it is like on a large, on a at a very general level, uh, but like I don't exactly know the details. We won't actually go into the mathematical details because that's way too complex for me at this moment. But we will like do implementation details, so like shapes and stuff, shape of like the data and all of that. And I'll be using like a lot of AI also for this because yeah, why not? Like the way Andrej Karpathy does it, vibe coding. I mean, we'll try to write a lot of code on our own, but like there's some stuff of this paper that I don't really want to work on implementing myself, like the unit portion. I mean, that's like an entire paper on its own, and I don't want to spend time implementing the whole thing, so I'll just end up copy pasting it. So yeah, so those are the kind of things that we'll copy paste, but some of the core portions of the paper I'll try to just implement myself, if I can, hopefully. So yeah, I just really hope my laptop can take this because streaming does take like an enormous amount of CPU load. So hopefully, yeah. I mean, my Visual Studio Code is lagging, so I might have to shift to Vim, which kind of sucks. But yeah, or maybe we'll do it in Sublime. I don't know. Okay, so I'll just open up the paper real quick. I had it downloaded like very recently. Okay, let's take the notes in just Vim, and then we'll do the implementation. And uh, We'll do the implementation in VS Code. I do have a couple of cool videos that I've made, which will probably release in a while. I don't know when though. Okay, so this is the paper. If you guys want this, you can download it. It's very popular. Just search for DDPM paper download and click on the archive link for it. Can this please happen? Okay, so now let's just read this and take some notes here and there of some of the more important sections of the paper. So DDPM. So there are few things that I would like to clarify. So the forward diffusion shapes, so like the input shape, the shape of the variables and the output shape, and then for the reverse diffusion, unet params, so like the hyperparameters. I want to know about the other hyperparameters. We can just write unet hyperparams. So these are some of the things we kind of want to know about. What is happening over here? Okay, why does it do that? So you did see me for a couple of seconds there. Was that happening because I was clicking on some key? I don't think so. Yeah, no, I think it's all good. I haven't streamed in a while, so yeah. Okay, so we have the unit hyperparams, and other than that, yeah, I also care about the output shape. I'm pretty sure I know what the output shape should be. It should just be the input shape, but still. And I mean, other than that, just some basic implementation details. But these are like the main things I wanna know about what is happening over here. Okay, so they do have some code. So introduction, deep GANs have generative adversarial and striking image, and okay, yeah, we'll kind of skip through this. So I mean, we all know this is our diffusion model work, so I'll kind of ignore that. So you can see that, so let's start from background. So diffusion models are latent variable models of the form this, where the latents are of the same dimensionality of the data. The joint distribution is called the reverse process, and it's a Markov transition starting at this. What distinguishes diffusion models from latent models is that the approximate posterior, called the forward diffusion process, is fixed on Markov chain that gradually adds Gaussian noise to the data according to a variance schedule. So we need to write out a variance schedule, and this paper does use a variance schedule. It's linear. Actually, no. I think the variance schedule is fixed for this paper. Like, it is a learned variance also, but yeah. So the forward process is where the variances can be learned by reparameterization or held constant as hyperparameters. So that's what is being done. So we are holding the variances constant. So I'll just write it down, constant variance. That's not a requirement. In fact, I'm pretty sure the stable diffusion paper has learned variances, but that's like a lot more code. And expressiveness of the reverse process by choice of Gaussian conditionals, because both processes have the same functional form or notable property, is that it admits sampling at an arbitrary time step t in the closed form using this particular notation. Okay, so we have this alpha, which is 1 minus beta t, and then we have this cumulative product of alphas up until the time step t from s. and then we just sort of have this formula. And pretty much, yeah, so we have all of the things for that, which is a good thing. So if we look at the forward process, let's go on to section 4 and check this. So we said t is equals to 1000. So let's just use those parameters as what they are doing. So I'll write some basic code. We set the forward variances as constant, scaling from this to this. So this should just be a linspace. Start should be 10 e negative 4, and it should be 0.02. Steps, I'm pretty sure, should just be equal to t. These constants were chosen to be small relative to the data scale from -1 to 1. Yeah, so that's another important thing. So data normalization is -1 to 1, so it's not 0 to 1, it's -1 to 1. Another important thing. Ensuring that the same functional form. So I'm guessing this is for like unit Gaussians. Yeah, so since we are, I guess we are applying like those Gaussians on the data and it has unit variance, that's why I guess we are having the -1 to 1 scaling instead of 0 to 1. The same functional form, bits per dimension. So to represent the reverse process, we use a unit backbone similar to pixel CNN with group normalization throughout. And then they use the sinusoidal position embedding, and then they use a 16 by 16 feature map resolution on the self attention. Oops. Yeah, so just do that. Other than that, what else do I need to look at? So they have given some additional details here, which is something I really want to see. Experimental details. So since we are implementing, we really mainly care about the experimental details. And I actually haven't taken a print out of the entire paper. And the funny thing is, I actually didn't take a print out of page 14, which is kind of funny because that's like the page we'll be referring to the most. Okay, but yeah, still, let's just read through that. Zoom in a bit. I hope you guys can see clearly. We replaced the weight normalization with group normalization, and the implementation is simpler. Our 32 by 32 moles use 4 feature map, and our 256 use 6. We'll make a small model. We'll just use this one. All moles have convolutional residual blocks, so they are actually having the residual connections, but I mean that's kind of optional. It's up to us if we want that. What else should we look at? Yeah, this stuff I'm not gonna look at because this stuff, I mean, it's gonna be unique to our stuff, so that's all right. We use a BDAT schedule, a set of constant, linear, and quadratic schedules. So we are using a linear schedule. To be honest, I mean, it does matter, but that's all right. So then they have a bunch of dropout values, and I'm gonna skip over that for now. Okay, other than that, I don't see anything. Let's just check. Okay, yeah, so that's pretty much it for that. So we still need to actually do this stuff. We need to actually implement the algorithm itself. So this is the algorithm that we need to sort of implement. And Okay, so how exactly do we calculate the, so we have the betas, so we can actually calculate the alpha. So we have this. So can we just calculate alpha t? Yeah. So we can just calculate alpha, which will be 1 minus betas. I'm pretty sure you can do that in PyTorch. Wow, it's taking so long for it to load. I haven't actually configured my Vim because I updated my laptop very recently, so I kind of lost everything. Kind of sucks. So, what was the name of the file? Model. Why is it taking so long, to be honest? I mean, it shouldn't. It's just 1,000. And as far as I know, this stuff works very quickly. Alright, so the next thing we need to actually implement is this. Let's exactly see what the exact formula that we need to implement is. Like, I'm pretty sure it's just this, but I'm not entirely sure. So this is for reverse diffusion. I think we should just upload the paper into ChatGPT and tell it what the formula for the forward diffusion is. I'd written it down somewhere once, but is it this one? Not sure. Why is this a freeze or something? Or did we mistype? No, it's just 1000. Or is it just that some subtraction is like a extremely slow operation? That's not the case, I know for a fact, but is that the case? Or is my terminal just freezing for some reason? Oh, why is that happening? Okay, that worked. So if we get rid of that, it's taking a while. I don't understand why, to be honest. Kind of weird. Okay, there we go, it worked. Ah, and I forgot to print out the shape, but to be honest, I mean, if it worked, that means it's all correct, so that's okay. So we have the alphas, and now the whole point is we need this cumulative product of the alphas. We also don't know what the loss function we need is. Yeah. I need the, what's the loss function? Optimizer is alright, but loss function is something I don't care about a little bit. Is there anything going on in chat? Doesn't seem to be, so that's alright. Okay. Now, if we go up, so we have this. So it's q of xt given x0. So this is what we want. So let's like just write a function for it, like forward diffusion. So for a certain time step t, we get the alpha, the beta. Do we need the beta? Yeah, we don't need the betas because we already have the alpha. Yeah, and in the formula they don't actually have the beta anywhere, so that should be all right. So we just need the alpha and the t. Yeah, so that should be good enough. So we can just do alpha bar is just equal to torch dot comprod alpha. How do you do comprod up until a certain thing? Is that it? Is that correct? I don't think so, but I think it's correct. I have to check how torch.comprod works. Wow, I have a bunch of tabs open. That just sucks because it's gonna lag. Yeah, I this is what I was trying. Cumulative product. So it does need dim. So I just need to specify dim 0. That's alright. So we'll just do that. Now the input shape is gonna be equal to, so the input shape, so like let's write it down in paper terms. So like the x shape is gonna be equal to batch by channel by height by width. So it should probably be this. So if we are multiplying this, then should we also have this scaled to that? Even if we are doing it for 1, the batch will just be 1. So should we do that? I mean, granted, I haven't actually made any provisions for input yet, but we'll do it with the mnist. So yeah. So what should we do about that? Let's just ask GPT, upload the paper. So this is what I usually like to do whenever I am implementing a paper, is I just open up GPT or Claude. I mean, with the new Claude model, it's so good. For me, programming wise, I prefer Claude a bit more than GPT. It can GPT a lot of the times it's very bad at actually using logic. Like it'll read the stuff and it'll be very good at reading, but it's pretty bad at understanding a lot of stuff. I think it's also because of the fact that Claude is a bit more specially trained on more reasoning data, and GPT is a bit more of a general purpose model. So you can't exactly blame them for that, but it's just my observation. And overall, I mean, GPT also lags a lot for me, so I don't really like that. Alright, let's just open up Claude and see if we can use that. I am using the free plan, so we won't be able to chat a lot, unfortunately. But I think we'll be able to do enough to just get the formula. But I do know that Claude has a very bad like formatting thing, so let's hope that's not a problem. Wow, it's taking so long for it to actually update. I'm pretty sure, yeah, my website just crashed. Wait, what? Length limit? This is literally a new chat. Or is it the fact that the paper is very large for that? So I guess we'll just have to use GPT because let's try again maybe if it works. And it was just lagging or something. Yeah, no. I mean, I at least need this much of a message, so I'll just use GPT, even though it sucks. Alright. Please just don't lag. Because whenever GPT lags, it's so bad, it just pisses me off a lot. Alright, let's see. Yeah, but you don't need to do record. Okay, yeah. So we have the varied schedule. Alright, so X0 shape is the one that I was talking about. XT should obviously have a retained shape. You typically pick a time step t randomly for each sample. Why are they literally they're literally giving us the code for everything? Come on, man. I want to do this by myself. I mean, I get it. Like I still. Okay, so we, like I said, see, I told you we needed this. We needed to view it like this because uh, since we are multiplying, we needed that. So yeah, I was at least correct on that part. All right, let's check the paper. this was the formula. So this is what they're doing, the square root alpha bar t. What was the alpha bar t again? It was just the cumulative product, right? The one that we just calculated. Yeah, this. So we have the alpha bar, and yeah, I think I'm gonna have to do this in Vim only, because I don't think I can open up VS Code right now, because square root yeah, I'm gonna have to first view that. But wait, what? That's weird. Why is this B? That's weird. So if you are multiplying with the x naught, how can you do this broadcasting? So they are saying t is b, but that's not correct, right? Because b is batch size and t is time steps. So how can we do this broadcasting? Why do we just have square root alpha bar t over here? Do we need that? No, we don't. So why do you have square root 1 minus alpha bar t? Oh, okay, this is the formula. That's why we have it. Alright, that makes sense. I'm not sure. Let's just generate the random noise first. So we can just pass in x naught, or is like x naught? I'm gonna have to check. Wow, so they don't have any examples. So input is a tensor. We don't have a device, so we don't have to pass that. So we just need to pass in x. Cool. But I mean, we are gonna be passing xt, right? Because we will only be passing in like x at a particular time step. Okay, I'll still write x over here, but I'm a little doubtful if that's gonna work. We'll see. I mean, that's alright. And to be honest, I mean, why am I passing that in as a parameter? The next thing I need to do is figure this thing out. How can this broadcasting even be possible? But wait, why are we trying to match the batch size? Can't we just have it to be T111? guess. Not sure though. Let's just ask it. Why does yeah, I know that. During training, we typically pick a random time step for each image in the batch. Why can't we do that? And of course, the website crashes. Yep, like I said. Let's give it a second. Yeah, there we go. So we did this correctly. Okay, I think we should do 1.0. Avoid any kind of data data type changes or anything. We want it to be floats. Okay, so they are saying we should just do the cumulative product outside. So we can just do the alpha bar outside. Alright, so let's just do that outside. I don't know why though, but that's the case. Time step per image. Oh, alright, okay. I think I got it. Yeah, we don't have a device luckily. So we got this correct. Alright, so so that's what it was. So we just had to do a -1 and then we do it like that 4-dimensional thing. That takes up a lot of space. Unfortunately, I don't have like that big monitor. Wish I did though. I really want one. I wish. Yeah. It's super helpful because I don't have to do this split screen. I have like a very small screen because now I have to kind of reduce the size of my window and it becomes less visible for me, and yeah, it's just a bit of a nightmare. Alright, so this is what we have. 1 minus alpha bar t. Yeah, this is supposed to be, yeah, so we first get the t. And this should just be alpha bar. Alright, other than that, everything is correct. Yep. And we are doing this for, if anyone wants to know why we are doing the view, because I was kind of vague on this, we just have to unsqueeze the dimensions to match the input shape, which we have written over here. So then we just do xt, and now this is just going to be straightforward implementing the formula that was given up top, which was this one. So that's just going to be bro, the variable names are so big for this. Alpha bar t times x plus 1 square root. I wish I had auto completion in this case. 1 minus alpha bar t times the epsilon, and oops, we just return xt. So that should do the trick. So we have a forward diffusion code over here, and hopefully it works. How do we test that? And I'm suddenly realizing that the paper copy that I've taken, the printout, is not going to be very useful at the moment, because the stuff that I've printed is mainly just theory. There aren't a lot of implementation details there, so yeah. So we now have xt. So if I had to do that, so let's just generate some random noise torch dot random dot random, and let's just do, I don't know, let's do batch size of 10, channels of 3, and a 28 by 28 image. So this is like a decent simulation. And let's just do forward, and let's do x noisy equals the forward diffusion, and we'll apply it for t, and we'll apply it on x. That should do the trick. Let's see. I mean, given the fact that it took so long to even run that single subtraction, I'm not counting on the fact that this should be quick. I also need my charger. Give me a second. I'll just get that. Yeah, I don't think this is executing quickly. Also, I hope you guys like the sound of the keyboard and everything. I got this new keyboard, and it's good because it's like kind of silent. Torch has no attribute rand n. What? Was it just torch dot rand n? I think. Kind of thinking I should have done this in a Google collab. Yeah, kind of. But I mean, I was a bit over my head. I thought I'd be able to get this quick. Apparently not. But yeah, whatever. Bro, this takes so much of time. It just sucks. I mean, I swear, bro, I'm like doing everything with this. Okay, yeah, it's just out of bounds because it's of size 1000, so we just need to do like a t minus 1. I was torch.random, not random.random. So that was another mistake. Rand like. Oh, I just spelled it wrongly. It's Rand. So yeah, bunch of stupid errors, but okay. Let's see if everything is like working correctly and stuff. We had a concurrent viewer apparently. Who just is 3, I mean, still good for me because I wasn't expecting anyone to be watching right now. It's pretty late. Cool, it worked. Alright, let's just see how much it worked. So let's do we only want to get the dot permute 0 2 3 1, and we only want to get the 0th one. Basically, because matplotlib needs the channel dimension to be in the end, and so that just does that, and then we just get the first image because you can't display a batch. We might have to convert it into numpy also, because if I remember correctly, matplotlib can't display a tensor. So we'll have to detach it and convert into numpy. It's taking very long. We aren't even doing any major calculations. I'm pretty sure these calculations are pretty quick. Okay, so we get some stuff. And obviously, I mean, it's random. It's it's just stupid stuff that we are seeing as we're seeing displayed. Because, to be honest, I mean, this wasn't supposed to look correct. Actually, that's why it's kind of a dumb thing for me to even plot this, because uh, it doesn't make sense for me to plot this considering the fact that we aren't actually using an actual image or something like that. We are just using like random data, so it just wasn't supposed to work. So I mean, but I do think that our code is correct for the forward diffusion. Let's just ask GPT, see if the code is correct. This is what I like to use GPT for. Is this forward diffusion code correct? I'll take a sip of water, just a sec. Alright, let's see. Please be correct. Okay. Just don't repeat the same thing. I know what my code snippet is. This is the thing I don't like about GPT. It generates like a very long response, and it generates a lot of like random stuff. Like, I don't want to know about this. It should be a little more concise. I'd seen like a couple of people on YouTube who tried this out with GPT, because even they were all like very pissed about the fact that it's so much of just fluff, and then only then you get like actual information. PyTorch.randent. What? Why are they doing this? I mean, don't you want to run it for the whole thing? Okay, wait. I'm gonna have to check a couple of things. What's the shape? Are we messing up on anything like that? I don't think we are, because I saw the matplotlib thing and it was 28 by 28 and it was colored, so that means we do have 3 color channels. Let's see if the batch size is correct, because we were messing around with this, so let's just hope that the batch size is correct. It should be 10 and this one was 1000. And even the permute was working correctly, so that's a good thing. Yep, that's correct. Okay, so this portion is correct. It's this part where it's a little messed up. So I have a good website that has implemented this paper, and I'm just gonna check how they did the time step stuff. Because wait, let's see. Wait, I think in the paper they had a thing about that. I think I remember where it was. Okay, I think I got it. So if you check page 4, they kind of talk about that. I mean, yeah, they kind of talk about that. Let me check. And also looking at that, I think I also saw another. I think I see another thing. I think the loss function is a mean squared error. I guess. Maybe. This is the one that I like. HO, that's like the short link. It's this GitHub repository. Probably one of the best repositories for neural networks. Believe me, like if you want to do implement some cool neural network idea, check this out. I mean, the only con is that it's all written in TensorFlow, so it's since we are doing this in PyTorch, we can't just straight up copy paste it. We might have to change a couple of things here and there, but other than that, it's probably got to be like hands down for me the best GitHub repository, because it's the supplement of the book, which I've mentioned quite a few times on the channel. It's a supplement of the hands-on machine learning with scikit-learn, keras, and TensorFlow. I have the physical copy of that book, and I've gone through it like quite a bit, and I routinely kind of open it up again and kind of go through it, and it's got to be one of the best like introductory books. I usually like to supplement it with like other blog posts and stuff, but it's literally it's so clear, and it's also it dives into a lot of fun stuff also, like some a little bit more advanced stuff and how to do production AI. Okay, let's see. Where is the auto encode? Not the auto encoders. Where does our nice little diffusion model start? That's the GAN. There's no way I was gonna train a GAN, but that's just raw. So the time is that. Then they're doing an A range on that. They're using this other variant schedule for some reason. I don't know why they're doing that. So they have like a more advanced variant schedule than ours. But to be honest, I mean, yeah, so this is their variant schedule. As you can see, the beta T, it's one of those, they have the exponential variant schedule, which was the one that was mentioned in the paper. A lot of people actually just end up keeping constant, but we are at least doing this much. So this is their data scaling, which we are just gonna do it uh, differently, so that's all right. So this is the T stuff. Then they are doing this stuff. Okay, but all right. So what I want to know is, uh, so they are batching it, then mapping it, and prefetching it right here. So the prepare batch method is basically the forward diffusion method. So this is what they are doing. Okay, so it is random time steps. Okay, so the GPT code was like a lot different than that. So even we need to do a random uniform for that. Which kind of sucks because why didn't they, why didn't GPT kind of say that? Which means I don't need that there. And we can just do a, what is alpha cum prod? So what does gather do? This part is okay. Wait, so T is x shape dot 0? Oh, okay. So for batch, you create the min val and the max val. All right. How do I do that in Torch? Wait, what? Wait. How do you do that? Wait, where's the repository? What is this? We want a very simple one. Let's just do this one. That seems like the most simple implemented. I don't think so. 1000 lines, are you kidding me? This is not a simple implementation at all. What the hell is that? Why have they... I don't know, bro. Bro, this... I figured this was like a basic implementation. This is not... This is like some crazy stuff. Definitely not what we are implementing. Not even close. If like just one guy has written this, then... props, I mean. Did it reconnect? Wait a minute, let me check on my phone. Are we still streaming? Just give me a moment, I have to check. Where can I check if I'm still streaming or not? And we also got a video call first. When I want stream. Why can't I have stream? Check on maybe. The new meeting is running. I think at the same point because we are really experiencing these many problems. Not. I don't know. I don't know. It's like I said. It's all very uncertain. All very uncertain at the moment. So I don't wanna say like this is like the last stream or this is like the last stream or stuff like that. I'll probably be putting out videos up until September, but after that, I don't think I'll have a couple of other commitments like university and stuff. So I may not be able to actually because I have to deal with all of that and yeah. So that will kind of take out a lot of time of my day and just overall that means I may not be able to kind of work on I won't be able to work on like that stuff. But it's not working and it's not responsive. Let's wait for a second.